Oh, you were in the previous class?
I was in the previous.
Oh, okay. Nobody's been showing up ever since I got everything online, which is the way I'm trying to design the course anyway, so I don't really know what the people look like that are in my class.
Oh, professor?
Yeah.
Oh, okay.
Yeah.
Sorry, sir.
So they know me from this copy, but I don't know them because I don't see them.
Oh.
Are most of the people from your class still coming now that, because is that the thermodynamics course you're in?
No, sir. This is Dr. Pittman with auditing, principles of auditing.
Oh, okay, that's right. It's the Monday, Wednesday, Friday that has the thermodynamics. Okay.
Take care, sir.
Yes, thank you. See, there we go. Now we're in focus. Hi, the lecture already started. I didn't realize it. I just went back to check with them to make sure they're recording. Today's lecture, this lecture, is Module 2, Lecture 5. We're still discussing data research design and data management, and we are progressing more and more into the discussion on statistics. But today's lecture is more related to experimental design and the crossover or interface with statistics, in that you want to make sure that you have a reliable comparison among or between and among your treatment groups, and that you're not making any errors. We'll talk about a couple of different errors. So the lecture that we're going to be covering in this recording is about sample size estimate and power analysis. But we have to talk about a few components of making comparisons or evaluating differences between treatment groups as we proceed. So most of this lecture material is coming from the statistics textbooks and research design textbooks that are either required or listed as supplemental textbooks or sources on the syllabus. So let's switch to the computer and begin evaluating this. So it is the Module 2, Lecture 5. And we recall this slide that researchers are determining differences between groups under study. There are three possible explanations: spurious association, chance association, which is still a major part of the focus of our discussions, leading up to causal association. And if there isn't time in this presentation, I'll make a separate presentation on the causal association that is the last series of slides in this lecture file. So the ultimate objective is to establish a causal association. So you must first rule out spurious and chance. And I want to make a clarification, as I was doing a bit more reading in some of our textbooks and sources and online sources, the links that have been provided to you through the WebCT, about the spurious association. We stated that this really is just a coincidence type of a situation and doesn't have any predictive value. In transitioning to our discussions about power analysis and sample size estimate, we will find that we can have significant differences between groups under study if we have extremely high ends. But what can happen is that you have very little power in that type of an analysis because it can be a very small difference. We're all familiar with the idea that as you increase your sample size in your different groups, then you're more likely to get significant differences between the groups because it just tends to bring your data tighter and tighter together. So you can have a small difference. If you remember those bell-shaped curves, if you have two very precise bell-shaped curves, very little variation, dispersion around the means, then you can fit them closer together and have the means be different, but only by a small magnitude. So it is possible to end up with a spurious association in some cases like that. One of the examples that I recall most distinctly was, especially with correlations, where if you evaluated the correlation between property loss and the number of fire personnel that show up at a fire, then you would determine that the higher the number of firemen that show up at a fire, the more property damage or loss that is incurred. So if your house was on fire, you might want to make sure that only 2 or 3 firemen showed up. Well, obviously that's a spurious association. In the case where you can have significant differences or correlations with the spurious association, it means that there has to be some other factor, some other variable involved in the overall treatments or events that are occurring that better explains that data. And of course, what we know is that the real correlation is that the magnitude of the fire, the amount of material that is burning, is more appropriately correlated with the property loss, and therefore you need more fire persons to come and try to put out the fires and save anything. So that was a good spurious association example that stuck in my mind. But we are trying to move past that. We have spent a good deal of time talking about problems and subproblems, trying to identify variables and determine which ones we need to control to stabilize our study so that we have a test factor that is the independent variable and an outcome factor that we measure that is the dependent variable, and we'll keep that in mind. So we have to progress from spurious association, where we rule out bias, we rule out confounding factors by all the methods that we've discussed so far, and begin to consider chance. But we want to have a predictive value to say, as I'm designing an experiment, I want to know that I can get a significant difference, and how large must the sample size be, and how powerful might that or relevant might that difference be? So there are some recommendations, and if you excuse me, I'm just going to get a copy of one of the sites and switch to the document camera to take a quick look at that. So this is one of the sites where I gave you the link on power analysis. I just printed it out for my own purposes, but there are a couple things that I did want to mention in just the very beginning part of it. Much of this is covered in our slides. But this I thought was a very interesting part. We will be talking about hypothesis testing. We, of course, talked about hypothesis testing from a scientific perspective, from your experiment. Now we're considering hypothesis testing from the statistical point of view, and they are different. And we'll point out those differences. So you can either have the reject support research, which is what we do mostly, or the accept support research. What it is associated with is either trying to reject, having as an objective to reject the null hypothesis. The null hypothesis is that the differences, or the difference between your treatment groups, two of them if you have them, or among your treatment groups is equal to 0, that there really is no difference. And statistically we approach it from that point of view, so that if we can't prove that they are all the same, then they must be different. And so we predict from statistics what the rate of error would be in drawing that conclusion, which of course is the opposite of our scientific hypothesis testing. We propose a hypothesis and we expect our research evidence to support it. So we want to support our hypothesis, not reject it. So society wants to control the type 1 error, and that would be that we would, as the example I gave of having a very high sample size and making a big deal about just a little difference between the two of them, and being able to say it's statistically significantly different because I have such a high N, it pulls in the variance. So society doesn't want us making claims that are untrue, based upon small differences between very, very large groups. There is a risk of over-interpreting small differences, small degrees of differences based upon that. The researcher must be very concerned with the type 2 error also, that you're possibly creating a difference when there really isn't one. So in this case, as I said, the high sample size works for the researcher. So if there's too much power, trivial effects become highly significant, and this is the point that I was making. So this is where the power analysis comes into play, and we'll see that an acceptable power level is around 80, and if we push for too high of a power, we may be misleading ourselves a bit with our data. So that's part of what we want to discuss today as we are moving from zero linkage, coincidence, to association. So both of these are included in the spurious association. The spurious association at this level, plausible or possible at one level, was our example of the firemen correlating, number of firemen correlating with the degree of property damage. And another variable involved in the situation will have to be evaluated to explain the correlation. So in other words, you couldn't make a causal association. So let's still just think about the chance association. It's ruled out by statistical tests. We do this by computing test statistics. I have a hard time pronouncing that, so I'll try to be emphatic every time I do it so I get it correctly. A number of this is a number computed from the sample data using some appropriate formula. The example that most of us recognize is the T statistics, the student T-test. We calculate a T statistic, In this case, we're thinking about an unpaired t-statistic that would compare the difference between the means of two independent groups. I present this information because ultimately we will define unpaired and paired analyses and grow in our understanding and appreciation for the distinctions and definitions of these terms. So this is an example, and all of us should recognize this formula. Somewhere in our mathematical education, we calculated a t-statistic where mean 1, I just have this here in terms to remind us that that is what the x bar sub number is referring to. So this would be x bar sub 1 minus x bar sub 2 over the square root of the sum of the standard deviation squared. We recognize this as the variance over the sample size in 1. So it's the standard deviation squared from the same experimental group 1 and the n, and the standard deviation squared from group 2 over the sample size, the n, for group 2. Hit the wrong button there. So what this tells us is that there are three components to calculating a test statistic. The first is, of course, a group comparison, the magnitude of the difference, mean 1 minus mean 2. The second is the variation within each group, and this, of course, is reflected by the standard deviation. The third is the sample size, obviously represented by the n's. So let's go back to our document camera and consider these first two, the magnitude of the difference and the variation within the means. And we go back to our illustration of a bell-shaped curve. If we have two groups of data, trying to keep these so that they're not skewed. And let's assume that we controlled, so we have a low bias and we have a pretty good precision. So what we're looking at is x bar 1 minus x bar 2, right? So that's our magnitude of difference between the groups, our effect size, as we'll talk about that later, and then these are our standard deviations, and of course the number of observations related to their frequency distribution. We know that the n is taken into account here somewhere. So this is what we're thinking about, and we convert these to bar graphs, and we know we would have the bar graphs. We'll say that this is a higher mu over here, so we would have group 1 and group 2, and the standard error bars like this. So the magnitude of the effect is the difference in the heights of the bars, the same as the represented by the distance between the two means there, differences in the mean. And then the precision is reflected, as we know, by the error bars. We project one over here and one down here. They do not overlap, so this is probably going to be statistically significantly different. So now we see our test statistic includes all of that information. The group comparison, the magnitude of the difference, the size effect, as we'll refer to it later, the variation, the standard deviation, and of course, we know somewhere reflected in that is the sample size. As you increase the sample size, let's go back just quickly to ask ourselves what would happen in collecting the same type of data if we increased the sample size. So we get our axis. I need to zoom out a little bit for this one. With a small n, it's going to look like this. So this is a low n. As we begin to increase the n, medium number, it would look like this. So this is a so-so sample size and a very high sample size, and we're assuming that the mean would stay the same in this case. but as you get to a very high N, it improves the precision, as we recall from our definitions before. Okay? But as you reach excessively high sample sizes, then you might be making it so precise that there's a problem of showing a difference when you really shouldn't be focusing on that difference, I guess is the point of view. But getting to this large sample size may be too costly in time and effort and obviously money and things like that. So it wouldn't be responsible just to do hundreds of thousands of samples, as you know, if you had to process them. It's not justifiable just to produce a difference where you want a difference. And this is, in essence, what we're considering here. What's a reasonable sample size, so you're not using resources in an unjustifiable fashion, and you are likely to get a difference that is believable and would be reliable. So to establish a statistical significance, you need the value of the test statistic, the student t-test, you need the t-test statistic, and the degrees of freedom, again where the sample size is represented, the degrees of freedom are the freedom of the n, the sample size, as we know. For the t-test, we know that it is degrees of freedom equals n minus 1, the sample size minus 1. And what we find is the p-value, the probability value, which is an alpha significant level, the probability of a type 1 error. So we're going to talk more about alpha significance level and the type 1 error as we proceed. You heard it mentioned in what I read from the printout of the website. And we'll define that in greater detail. Then we go to tables of values, which are frequency distributions. There are 4 types of these. We're not going to define and use all of them. There's the z-normal distribution, the t-distribution for the student t-test that we're familiar with, a chi-squared that we won't deal with, but you may have worked with in the genetics lab as an undergraduate student or in other situations, and the F table, the F distribution, which we will talk about when we talk about the analysis of variance. So what do you get then? You determine the probability of obtaining some value of your test statistic or greater for a given sample size. So again, the sample size becomes very important. It's reflected in the degrees of freedom when you go look up the table. The p-value is the probability that a test statistic as large as one obtained from the data could have occurred by chance when no real difference between the groups existed. So, for example, if p equals 0.05, that's 1 in 20 chance, or a 5% chance that you made an error in saying that there was a difference or observing a difference when there really was not a difference. So we're beginning to see that errors can be made in one direction or another. So let's continue building our appreciation of some things that we're familiar with before we get into those definitions. So if we say that p is less than or equal to 0.05, the results are statistically significant. In most individuals' mind, and the sciences especially, that's just barely. That's the minimal probability that's acceptable, risking, if you will, 20 errors out of 100 is, 1 out of 20, or 5 out of 100. I obviously use computer programs and spreadsheets and calculators to double check myself. So this is accepting that you may have an error 5 out of 100 times. It'd be more likely, 50 out of 1,000 or something like that. But that is why it is considered as the minimal cutoff point for most of the types of studies that we would be involved with in biology. and it's rare that anyone will accept a significance level any difference in that. You may sometimes see a 0.06. We saw a 0.02 in one of the graphs in another graduate course in neuroendocrinology that I'm teaching. It's still less than 0.05, so it is acceptable, but the most common ones are 0.05, 0.01, 0.001, as we know and as we'll see. So you have to meet at least this to conclude that there's a statistically significant difference between the groups, ruling out chance as an explanation for your observation. So the statistical power then is defined as the likelihood that differences of given magnitude will be found statistically significant in a study. So this is what we're saying. If you decide that the magnitude of your difference is going to be small, then it is going to ultimately lead you to requiring a very large sample size that you have to estimate separately to demonstrate that you have at least an 80% probability of that to be a significant difference. Now, whether it's a real difference that we should give any attention to is another aspect of the distinction between statistics and the human mind, the human brain, to differentiate what's real, what's important, and what actually matters, and not to end up focusing on trivial things, if you will allow me to phrase it that way. And certainly reviewers on grant proposals would phrase it that way and possibly more harshly. So it gives you a predictive power. It's expressed, as I said, as a probability, 0 to 100%. 80% is the cutoff. Any power less than 80% is not credible. Any power 80 and above is credible. And as we said, as that power increases, you have to begin to ask yourself, how large is the sample size and how big is the magnitude of difference? Remember that two of the three matters that we had mentioned in the test statistic. So it's important in the consideration of the design. Actually, you're supposed to perform a power analysis and a sample size estimate, either based upon known information, either established in the laboratory you work within or from the literature, possibly, and most frequently, or pilot studies. So we talked about thinking through your problems and subproblems, objectives and aims, and coming up with a reasonable design such that you control for any predictable or anticipated matters related to variance and bias, the confounds and things like that, so that you can collect some data and get a small sample data set to begin making comparisons to determine whether it's feasible. You can take that information, as you'll see, and feed it into formula or statistical software packages and perform a power analysis and an estimate of the sample size that you would need to have a reasonably statistically sound analysis claiming or stating or supporting that there is a statistically significant difference between your treatment groups or differences among your treatment groups. So we'll talk just about the sample sizes for hypothesis testing. There's sample size for proportions and intervals. Most often we as scientists work with hypothesis testing. This is challenged. Actually, the authors, and I don't know who the authors are, it's StatSoft Incorporated is actually the site that we list. And that site emphasizes that interval estimates are the way to go, and discusses the reason for that. I don't think we're going to change the way we do things in science quite that quickly. So we really need to focus on the hypothesis testing. So as indicated in table 4.2, there are 4 possible outcomes at the end of experiment. We'll see that table in just a moment. When the null hypothesis is true and one accepts the null hypothesis, we fail to reject it, that is, then one has made a correct decision. Okay, so again, remember the null hypothesis. When we talk about hypothesis testing in this sense now, we're talking about statistical hypothesis testing, which means that you state the null hypothesis as the differences among your groups equals 0, that they are all the same. And if they are all the same, there's no statistically significant different comparison among all of them or between the two, if you're only looking at 2, then the null hypothesis is supported, and it is opposite from what you want scientifically when you are going into it saying, if I do this, I'm going to either make this, change this test factor, my outcome measure is either going to be higher, greater than, or less than my control group. But when you go to the statistics, it's actually testing the null hypothesis of whether they're both the same. So if they're not the same, then something must be different. So this is the way that it is approached mathematically, statistically. It's the opposite from our scientific intuition. But it's fine. We can go on and do our studies the way we are normally doing them, run our statistics, and keep thinking, okay, when I get my results, if it says it's significant at p less than 0.05, they're different, and I interpret them based upon the direction and magnitude of the difference between the two, like we always do. We're not trying to change that. We're just trying to have you understand what this means, hypothesis testing in the sense of statistics, of course, versus when you're discussing in general experimental design and setting up your hypothesis to test with your experiment. The data gets analyzed statistically, and we ask first whether they are all the same, so the differences are not greater than 0 statistically, so we would fail to reject the null hypothesis. Wouldn't make us happy, but that's one of the possible outcomes. But if it's true, if we fail to reject it and that's true, then there really is no difference between our treatment groups. Similarly, if the null hypothesis is not true, and hence some alternative hypothesis holds, so the statistical alternative hypothesis is actually our scientific hypothesis saying there is going to be a difference, and one rejects the null hypothesis, then one has also made the correct decision. So this is what statistics are going to tell us. There is not a significant difference between them. Their means are so close that they look like they're equal. The difference is, actually 0 statistically. Or the means are significantly different, or the magnitude of the effect, the difference between them, is robust enough that we can consider them as not equaling 0 when we compare the two means. Therefore, we reject the null hypothesis that's claiming or wants to say that their differences are so close, the means are so close together, it looks just like 0. Then we have the effect that we're thinking of statistically, and we support the statistical alternative hypothesis, which is in agreement with our actual hypothesis. Now, when we talk about experimental design and writing grant proposals, you have to come up with an hypothesis and say, what will you do if you don't get the data that you're, the outcome that you're expecting? What will be your alternative interpretation of this? So in science, we do have a hypothesis and an alternative hypothesis. The hypothesis is the one that we want to happen. That's what we really think is going to happen. But if we don't get the data to support it, we have to interpret the data in some other way and try to explain it. That's all our alternative hypothesis. So it's pretty much the very different situation statistically, mathematically. So please keep that in mind. So the null hypothesis is therefore equivalent to the secondary hypothesis. What we'll do if we don't get the data that we expect, because we would have to go that way, saying we didn't get a statistically significant difference. Statistics is seeing the differences more like 0 than not like 0, so we failed to reject the null hypothesis statistically, so there's really no difference. How do I interpret this? What is my other explanation, my alternative scientific hypothesis? But statistically, our initial scientific hypothesis is our statistical alternative hypothesis. We want to reject the null hypothesis and thereby support our alternative hypothesis statistically. Then we can say, yes, the data supported my scientific hypothesis that predicted there would be a significant difference between or among the treatment groups. If that still seems very confusing to you, you can go to our textbooks and read it, and it may remain confusing, but you need to establish that understanding in your mind. The most important description of hypotheses that you need to keep in mind in science are the scientific hypotheses. Your working hypothesis, the one that you pulled out of that gap from the theoretical framework, asked a question, answered it, and you got your hypothesis basically. And if that isn't supported by your data, then you have some other alternate way of explaining it, your alternative hypothesis. That's the most important one that you need to understand. But now that we're talking about statistics, it is mathematical and it's a bit different. So let's push on. Enough of that, right? So let's think about sample sizes for hypothesis testing. And as I said, we're trying to discuss these first, and then we'll see how it's done and look at a formula and take it from there. So there are two erroneous possibilities, so we're still thinking of those four. So now we'll start talking about the errors. So if the null hypothesis is true and one incorrectly rejects it, then one has made an error of a false positive. So now we're starting to get to this definition of the type 1 and type 2 error and so on and so forth. So you can make an error of a false positive where you're saying there is a difference when indeed there truly is not a difference. And this is what can happen if the sample size is so tremendously large. You have a magnitude of difference that is quite small, but you basically have forced the statistical test to saying that it is significant. That can produce a false positive error. Alternatively, as well, if some alternative actually holds, yet one fails to reject the null hypothesis, then one has made an error of a false negative. So it's possible to make an error of false positive and an error of false negative. And it's important to understand these as we proceed to discussing power analysis and appreciating the terminology that is used. So here's that table 4.2 from our textbook. The decision process and hypothesis testing. This is statistical hypothesis testing. And we say, what is the state of nature or the truth? Then we look at decision made, null hypothesis as being true, and the alternative hypothesis as being true. So if we accept the null hypothesis and it is a correct decision because the null hypothesis is indeed true, then everything is all right. That's the first of the four outcomes. If we accept the null hypothesis, but the alternative hypothesis, statistical hypothesis, is actually true, the scientific hypothesis that we believe in, we believe our data is going to support, is true, but the statistics fail us, then it's possible that there's a false negative. So something was wrong somewhere along the line, our data didn't turn out to be statistically significantly different, and now we're saying our hypothesis, our scientific hypothesis, is not supported, but indeed it really would be different. Who knows what might be, didn't control for bias and variance and all those types of things, and your data just wasn't clean enough. or your sample size wasn't large enough, even though it wasn't outrageously large, it was still too small to do that, you can have a false negative. The opposite, where you reject the null hypothesis because the alternative hypothesis is true, that would be a correct decision. And this is what you would like to have happen in your experiments, where you test for the null hypothesis with your statistical test, and you're hypothesizing that the difference between the sample means is so close to zero that statistically it looks like zero. If you reject the null hypothesis correctly because your experiment is done right and your scientific hypothesis is correct, you make a correct decision and your data supports your scientific hypothesis. If, however, something went awry, either purposefully or not purposefully, maybe one day you did your control group and you had the setting on your instrumentation calibrated properly, you get lower values, go in the next day, somebody was messing with it, you didn't recalibrate it, and you get higher numbers for all your experimental treatment group. You go through the statistics and you reject the null hypothesis, but in reality the null hypothesis is true. If you had calibrated your instrument, then there would be no real significant difference between the two treatment groups. Then you have a false positive. So the risk is in having false positives or false negatives. So the power analysis and the estimation of sample size are exercises required prior to executing the full-blown experiment. You can do some pilot studies first, but prior to executing the full-blown study, in the proposal, you must perform a power analysis and an estimation of sample size to justify your experimental design such that you're reducing the risk of a false negative and a false positive. And this is what all that discussion about the bias and the confound, controlling variance, and the bias being the difference between the population mean and your sample mean, controlling for all of that information so that the data again is accurate and reliable, and when you draw a conclusion, hopefully in this direction where you really have a difference, you've rejected the null hypothesis because you truly have a difference between your treatment groups, which is the alternative hypothesis statistically, and you go on to say the data supports my scientific hypothesis. That's what we all want, and we want that to be a correct decision, not a false positive, or we don't want to end up saying that our data doesn't support my scientific hypothesis and have that be a false negative. So we don't want these risks to occur. We want the right thing to happen. So continuing on to determine the sample sizes for statistical hypothesis testing, there are the two erroneous possibilities. So we want to state these a few times to redefine terms as we go along. If the null hypothesis is true and one incorrectly rejects it, then one has made an error of a false positive, which is also called a type 1 error. If some alternative actually holds, yet one fails to reject the null hypothesis, then one has made an error of false negative, the type 2 error, as we saw. So now we've just added this terminology, type 1 error here and type 2 error here. So the false negative is a type 1 error, the false positive is a type 2 error. We'll see that we assign an alpha value to this one and a beta value to this one. Alpha value is what we determine to be an acceptable probability of risking this. The 5% is what we saw before. We are comfortable with risking a 5% error when we say p less than 0.05 is a statistically significant difference. So we have set our alpha level for a false negative. If we set that at 0.05, as we'll see, the false positive has to be set at 95%. But we said the power analysis is going to focus on the false positive, and an 80% is a comfort zone. It is the cutoff point. We'd like to have it higher, but not so high that we create a difference when it truly doesn't exist, and we start pushing in this direction. So we have the type 1 false positive alpha error and the type 2 false negative or beta error, and it's desirable to limit the rate of such errors. We have a social responsibility to limit these types of errors so that we don't mislead the general public, the scientific public, the professionals in our discipline and our colleagues and so on and so forth. So we don't want to misinterpret our data because we play with the sample size and all of these factors to create a difference when there truly is not one, or to have any other type of error. So the basis of the sample size calculations in statistical hypothesis testing is to specify an allowable rate of false positives, as I said, the type 1, and the alpha value, and an allowable rate of false negatives, the type 2, the beta value, for a particular alternative hypothesis, our scientific hypothesis that we want to study. We are actually testing with our experimental design. And to estimate a sample size large enough so that these low error rates can be achieved. So again, it's this balance between the power and the sample size such that we get acceptable risk levels for error, and we don't create a difference when a difference doesn't truly exist. So what is the alpha and beta again? So it's that allowable rate of false positives that is called the level of significance, or the alpha value, the type 1 error alpha at 0.05. So when you write a grant proposal or a research article, or read a research article in a grant proposal where statistical analyses are included, somewhere within there, under the methods for a research article and of course the methods for a proposal, it has to be stated that the P or the level of significance was set at P less than 0.05. This is the standard statement. Everybody uses it. The reason we use it is because we're obligated statistically to set our alpha value at a reasonable value. And the 0.05 is the one accepted. So when you write a proposal or a research article where statistics was included, damn well better be included, you will state somewhere within the methods the level of significance was set at P less than 0.05. You are telling the audience, that the readers, that you set your type 1 error, the false positive, back to our table there, the type 1 error here, excuse me, the false negative, you're setting that at 0.05. So describing the rate of false negatives, use the terms, when describing the rate of false negatives, we use the terms as the probability of rejecting the null hypothesis when the postulated alternative hypothesis holds and a correct decision is made. So it's called the power of the statistical test of significance, or the type 2 error, that is the beta value that we're seeing set at 95. So we don't see statistically reported the type 2 error rate because after the statistics are completed on the full data set, it is convert this to a percent, 5%. It is the difference between your alpha value and 100%. Or with decimals, alpha plus beta must equal 1. So beta equals 1 minus alpha is another way of looking at it. But we're talking about setting a beta level for a desired power of minimizing the type 2 error. So the sample sizes for hypothesis testing, clearly it's desirable to limit the rate at which such errors are made. So we remind ourselves of this, reiterate that. So in fact, the basis of sample size calculations and hypothesis testing is to specify an allowable rate of false positives and an allowable rate of false negatives for a particular alternative hypothesis and to estimate a sample size large enough so that these low error rates can be achieved. So the allowable rate of false positives is called the level of significance, sometimes referred to as the alpha level. So summarizing what we saw in the last couple of slides. So the level of significance was set at p less than 0.05 is the phraseology that you want to have implanted in your mind to put into research proposals and research publication articles or reports. So in describing the rate of false negatives, it's often described in the terms of probability of rejecting the null hypothesis when the postulated alternative holds and a correct decision is made. So this is a definition of the power of the statistical test of significance. And I realize we're saying things over and over again, but it's progressing toward establishing definitions. So the type 2 error is beta, which is related to the power of the statistical test of significance. So the alpha level or level of significance is often set at values of 0.1, 0.5, or 0.1, rarely at 0.1 for any type of work that we might ever do. That's accepting 10 errors out of every 100 trials, not good for anything that we would do. You will most likely through your entire career use nothing but the 0.05. Now this doesn't mean that once you complete the statistical test that it tells you that the significance is at a probability, a p-value less than 0.00001. It just means that you set beforehand this critical value of alpha, which you will use as the cutoff point. If it isn't less than 0.05, then you will not consider it to be statistically significantly different. This means that if you run a statistic test and you get p equals 0.05, then you do not consider it as significantly different. It has to be less than. We're not saying p is less than or equal to 0.05. We're saying that that's 5 out of 100 is the acceptable error level, but I'm going to set it less than that so that it is a better comfort zone. So the power levels are usually at or about 80%, 80, 90, 95, etc. So the sample sizes for hypothesis testing then, as with the two criteria for sample sizes and confidence interval estimation, the two criteria for sample size estimation in the hypothesis testing context, the false positive rate, power, work at cross purposes. So in essence then, one can make a false positive rate low by making it very difficult to reject the null hypothesis. In an informal way, we can say that this means that we require quite a bit of evidence that the null hypothesis is false in order to reject it. However, if we do this, then it will be difficult to reject, and hence the study will have low power. So you make it too difficult to demonstrate a difference, and you'll have a low power outcome. So conversely, if we achieve high power by making it easy to reject the null hypothesis, we will inflate the false positive rate. So here is what we had discussed before, trying to get a balance so that you have credibility in your data is really what it comes down to. You see the graph, you look at two things whenever you see graphs and there's 2 points being compared. You look at the distance between the two of them. You also want to look over at the scale too, you know. a difference of 1 between two sample groups. If your y-axis is at a scale, let's go and take a quick look at that. If you've got, and most of you hopefully understand where I'm going with this, if you've got what looks like a big difference between these two, and you see that this is 1 and this is 2, and really the only difference between these two is a unit of 1, you have to ask yourself, is this a large enough magnitude of effect based upon the phenomenon being studied and your insight into the biological system under question? Is that a large enough magnitude of difference to be important? So regardless of what the error is in this, that's for experimental error, the variance terminology is not a good one to use. Regardless of what the variance might be, you have to ask yourself, is this a real difference? So say this, the ends would be shown here, and this is 1,000, and this is 1,000 also. So you have an extremely high N and a small magnitude of effect with pretty tight variance, then you know that you might be risking a low power comparison. So the type 2 error. So in estimating the sample sizes in the context of the hypothesis testing, you want to strike a balance between the false positive rate, the power of the study, and the sample size. So we'd love to have a study with very low false positive rate and very high power. This will usually require a large sample size and may not be practical. So in designing studies, we can assess the costs of various trade-offs in these quantities and select the combination that is most suitable. So if you have relatively expensive samples and you proposed an N of 1,000 each, obviously the funding agency is going to think that something's up, and you're asking far too much money to perform the experiment than what might be necessary, and they begin looking at whether you've got a power analysis, but your sample sizes and preliminary data, and may not do it by all the mathematical methods, but with scientific reasoning can reach the same conclusion. You're trying to create a difference where a difference probably doesn't exist, and it's just too costly, and it might not be an important enough of an outcome measure to focus on to justify the expense. So determine the sample size necessary to achieve adequate power for detecting a difference among your study groups. You need to know the following. So in determining sample size, the estimated level of the outcome variable that you expect to find in your control or reference group. The reference group is the standard or control treatment in clinical trials, the control group in case-controlled studies, or the group without the risk factor in the cohort studies. So the control group, and none of these are probably the types that we'd encounter, but anyway, we understand our control and treated groups. So you can estimate the outcome variable, usually a mean and standard deviation, or a proportion. Mean and standard deviation is what we'll focus on, by using values from previous studies and literature, from your own clinical experience, or laboratory experience, or in the absence of prior estimates of the outcome variable, you can conduct a pilot study, which is most commonly what we would do. You need to know the effect size, the size of the difference between the groups that you would consider clinically meaningful or important, the significance level, p-value. This is that alpha we were talking about, 0.05, the level of power, at least 80, so you run it at 80. And as an example, we wish to conduct a randomized clinical trial to study the effects of drug X on blood coagulation in patients with coagulopathy. Patients with drug X treatment group and those with placebo controls will be compared with mean on the basis of mean prothrombin time, or PTT, which is what this is supposed to be down here. I don't know how it got converted to all the I's. From previous clinical studies, we know that the average PTT in such patients is 17 seconds with a standard deviation of 4 seconds. So again, this is an example of being able to know or predict what your control level would be. So we'd like to see at least a 1.2 drop in PTT with drug X before we consider it to be clinically effective. So scientific and biological clinical reasoning to say this is a magnitude of effect that really would be of value. You see that it's only 1.7, but it's 1.7 seconds longer to coagulate, basically, which for me would be more important to stop my bleeding faster. Kind of a way to think about it. Clinically, obviously, it's very relevant as well. So at a power of 90 and at a significance level of 5. So they're using the 0.5 and decided to go with 90. So to use the table D3 from the source, you'll see that in a moment, we first need to define the quantity D prime that appears in the table. This is merely the difference in the means we wish to detect. The effect size divided by 2 to the negative 2 power times, let's just look at the formula. D prime equals the difference in the means over the square root of 2 times the standard deviation. Here's what we got, the effect size of 1.7 seconds, right? Divided by the square root of 2 times the 4, the standard deviation we come up with. It gives us a D prime of 0.3. We looked this up on the table for P equal to 0.05 and the power of 0.9. We find the required minimum sample size to detect the difference of this magnitude with this degree of variance, standard deviation I know, would be 117 patients per group. And so notice that in the table the power is referred to as 1 minus beta. So here we see this is the D3. This is the sample sizes per group for testing the differences in 2 means. And this one is actually setting alpha at 0.1. So I wanted to show both tables, alpha at 0.1 or alpha at 0.5, the next one. And we got a 0.3. And so to get this goes 70 to 90, but to get 90, if we set alpha at 0.1, it'd have to be 166 in each group. This is the 0.5 that was described before. The 0.3 would have to be 117 to get a 0.9 power, 90% power at an alpha of 0.5. But look what happens as this number increases. So as we get to a 1.4, so remember our formula of the difference between the means, the magnitude of effect, as this increases and or variance decreases, then you can have quite small sample sizes, that's 70, quite small sample sizes around 8, 6, or 5 to have an alpha at 0.1 and still have a power of 90. So again, it goes back to what we started with in this lecture of the 3 variables or the 3 factors that really matter in getting at this idea in the first place, and that is the differences between the means, the standard deviation, and the sample size. And we see how they interplay on this table. There are software packages that can be used to do this. One that I demonstrate here, just captured the images as GraphPad. I really like this program overall. I gave the information. So here we're doing a sample size estimate to compare 2 means with an unpaired t-test, alpha at 0.5 and a 2-tailed. We'll define unpaired and 2-tailed and 1-tailed later as we get into statistics. And we just put in the standard deviation of each group, and we're assuming that the variance is equal in each of them. We got everything under control. So here you see the outcome. I've got this on another table. But here you see the power. So you'd have to have a magnitude of difference, the difference between the means, of 14.56 if you only had 3 per group. To have about 8 per group at the 80% cutoff, you'd have to have a difference between the means of 7.55. So this one is kind of telling you if you accept a level of variance between the 2 groups, set alpha at 0.5, your beta at 80, your power at 80, then Can you get this type of a difference between your groups? You have to have pilot data to know if you can achieve that and see what your sample size would be. This is that whole table. So if you look, the N per group as it increases to get to the 80, here's the 80, then the difference between the means becomes smaller and smaller. And this is true in the case of each of these, but as you get to higher powers, then that difference has to be a little bit larger, even with a large sample group. And then finally, a power analysis where we compare the means with the unpaired t-test, again testing the null hypothesis that there's no significant difference. Here we put the sample size for the two groups, the standard deviation, alpha at 0.5, we're doing a two-tailed. I know all that doesn't make sense to you, but this here at least you recognize. You'll come to understand and appreciate these later to perform this type of an analysis. So here we see the difference between the groups and the power. Let's just go to the next slide that shows those. So the difference that we would have to get to have a power of 80 would be 4. So in essence, this is how you utilize this information. As I said, I'll do a separate lecture on causal association to complete this. For now, I'll stop here, and I appreciate your time and attention, and look forward to seeing you again soon.